Welcome to the 14th lecture in our particle characterization course. In the previous lecture, we discussed structural characterization of a particle and pointed out that essentially the structure of a particle can be divided into three regions: the surface, subsurface and core. Of the three, the core is the purest representation of the material itself, including its defects and so on. The subsurface is the region that shows a fairly gradual transition between the surface and the interior of the particle, but the surface region really is the one that is most exposed to the exterior environment. The external surface represents the planar, or actually as we saw, the volumetric interface between the particle and the fluid in which it is immersed. And therefore, from the viewpoint of how a particle interacts with its surroundings, the surface really plays the most crucial role, and therefore it is important to understand certain surface properties of particles. So, in this lecture we are actually going to look at three of them: surface energy, intermolecular forces of adhesion, and adsorption of fluids. These are probably the three most key characteristics of how the surface of a particle interacts with its neighbors as well as the medium in which it is suspended. Now, the first aspect, surface energy, it is something that it is a term that we hear frequently: surface energy, surface free energy, or even surface tension. They all mean the same things. Now, surface tension of a fluid is something that you are all quite familiar with from your lessons in fluid mechanics and so on, but particles, whether solid or liquid droplets, also have a surface energy associated with them. Now, the surface energy can be defined as the energy that is left over when the particle is created. In other words, the higher the surface energy of a particle, the greater is its tendency to react with its environment because it is in an energized state. Just like a low surface tension fluid tends to have very little interaction with surfaces that it comes in contact with, similarly a low surface energy particle or droplet will be relatively inert compared to a high surface energy particle. Now, this has interesting implications for the manufacturing industry, because sometimes you want particles that are highly energized, that have high surface energy, and sometimes you want particles that have relatively low surface energy. It all depends on whether you want the particle to remain as an isolated particle and not interact heavily with its environment, or you actually want the particle to behave in a cohesive manner with its nearest neighbors as well as the fluid molecules that it comes in contact with. So, the definition of the surface energy parameter is something that we need to be aware of. The surface energy definition goes back to creation of the particle surface. What is the irreversible work involved in creating a surface? This energy is what is referred to as the surface energy of the particle. So, if we look at the creation of let us say a surface dA of a particle, a differential surface dA. So, this is the new surface that is created. Then gamma times dA is the irreversible work associated with creating the new area or new surface, where this parameter gamma now is the surface energy or surface free energy or surface tension associated with the particle. So, what is this gamma dA equal? thermodynamically speaking, this equals dE minus TdS minus summation over I of Ni d mu I dNi, where this parameter dE is termed the surface excess internal energy. ds is the surface excess entropy, mu I is the surface excess in chemical potential, and dNi is the surface excess in number of atoms. So, this thermodynamic relationship gives us the context in which you relate surface energy with parameters such as internal energy, entropy, chemical potential, and also number of atoms that are on the surface. When we talk about excess, what we mean is the delta between these values at the surface compared to their values in the bulk of the material. As we will see when we discuss nanoparticles, the reason that nanoparticles get their properties is because in a nanoparticle the differential can be quite high. A nanoparticle tends to have many more of its atoms on its surface per unit area compared to larger particles, and that is the reason why nanoparticles are so much more reactive compared to larger sized particles. But it basically goes back to this equation. Now, there is a parameter called the Helmholtz free energy F, which is related to the internal energy by E minus Ts, or in other words you can write dF equals dE minus TdS minus SdT. So, you can go back to this equation for gamma dA and substitute in terms of the Helmholtz free energy, and you will get dE minus TdS equals dF plus SdT minus summation over I mu I dNi. From this, the definition of free energy follows. So, gamma is defined as del F over del A at constant T, constant Ni, and constant volume. So, when you keep the temperature constant, this term drops out, the SdT term drops out, and when you keep Ni constant, this term drops out, and the requirement of constant volume basically refers to the fact that you are essentially considering a volume which comprises of the particle and the fluid which is in interfacial contact with that particle. So, this is the conventional definition of Hammacher constant, and this is used in a theoretical sense to calculate gamma if you know the free energy, the Helmholtz free energy associated with the formation of the particle. Now, in an experimental sense, this is not how you determine surface energy of a particle. The surface energy of a particle, just like the surface tension of a liquid, is really determined by looking at how it interacts with the fluids and other particles in its vicinity. So, for example, if you have a high gamma particle and you bring a surface in contact with it, the sticking coefficient or the adhesion force is going to be very high. Similarly, if you take a high gamma particle and you bring another similar particle close to it, again the interparticle cohesive force is going to be very high. So forces such as adhesive force, cohesive force actually scale as gamma. As gamma values increase, these forces of interparticle interaction as well as particle to surface interaction will increase. And of course, correspondingly the wettability of the surface of the particle when it is interacting with the fluid will also increase. So the higher the surface energy of the particle, the more likely it is that you will get good wetting of that particle by a surrounding fluid. Again, the counterpart to that, if you think in terms of liquids, if you have a high surface tension liquid, then it is likely to have good contact with the surface that it is spread on, whereas a low surface tension liquid will tend to bead up. So surface energy for a particle plays the same role as surface tension for a liquid in many ways. There is a parameter called the Hammacher constant, which we will look at in more detail later on. The Hammacher constant is one that is used to describe intermolecular or interparticulate forces under conditions where only the molecular level interactions are present. In other words, there is no surface tension forces, there are no capillary forces. In that case, in the so called dry state, it is only the van der Waals forces that are in effect, and they can be represented by this Hammacher constant H. And we will see later on that there is also a one-on-one relationship between surface energy and the Hammacher constant. As the surface energy increases, the Hammacher constant tends to increase, and as the Hammacher constant increases, there is a corresponding increase in the interparticle forces of adhesion in a dry state. So when we are looking at various materials and ranking them with respect to their adhesion potential, the Hammacher constant is usually taken as a reference value because it has such a close relationship to the surface energy parameter gamma. Okay, that leads into our discussion of what we mean by the intermolecular forces. In our context, let us call them interparticle forces. Again, the differentiation between molecules and particles is very fuzzy. A particle is basically an aggregate of molecules, and it is really up to you to define when you stop calling something a molecule and start calling it a particle. But many of the discussions that we are going to have apply equally well to molecular interactions and to particulate interactions. Now when you have two solid objects, whether they are molecules or particles, or even two liquid objects that are discrete entities, when you bring them close together, they experience two kinds of forces: adhesive force and repulsive force, right? Now, so what happens is the two particles, as they approach each other, are experiencing these two opposing forces. So eventually they will reach a state of equilibrium that represents minimum overall force or potential on these particles. That is considered their equilibrium position, and the two droplets or particles will then essentially sit at these positions and kind of oscillate, right? Or if you have a surface that a particle is approaching, the surface will remain stationary, the particle will establish an equilibrium position above the surface and then will essentially vibrate around that position. So this equilibrium position at which you have a minimum in the intermolecular energy potential is a key parameter that dictates how close a surface can approach each other. And this has huge implications in many manufacturing industries that rely on maintaining a certain space between two virtually contacting surfaces. The interparticulate interaction in the dry state is also called the 612 potential. It's also known as the Leonard-Jones potential. And it basically says that if you have two particles that are next to each other, the potential that they develop between them can be written as a minus a by r to the power 6 plus b by r to the power 12, where this is the attractive component and this is the repulsive component. Of course, the reason they are called the 612 potential is because of the exponents of r in this equation. The adhesive force or the attractive force will fall off as the 6th power of the distance between the surfaces, whereas the repulsive force will fall off as the 12th power. So what that means is, as the two surfaces move farther apart, the attractive force becomes more predominant, whereas as they move closer together, the repulsive force becomes more dominant. And that is the reason that, I mean, it's basically as you move away, the surface pulls you, as you move closer, it pushes you, right. So obviously there must be an equilibrium position where the two perfectly balance each other. And in fact, if you plot u as a function of r according to this 612 relationship, the kind of curve that you get will look like this. And this distance, so this is your 0 point, this distance of separation at this minimum energy point or minimum potential point is your equilibrium distance of separation between the two surfaces, because that results in a minimum in the potential energy between the two surfaces. So the surfaces will have a natural tendency to settle down at this distance of separation, and the depth of this energy well, which is written as epsilon, is also an important parameter. This represents essentially the potential energy barrier that must be overcome in order to get these two particles to attach to each other or to peel them off from each other, because again the equilibrium position is the most stable position. So if you want to disturb a particle pair from its equilibrium position, either way, if you want to push them together or you want to pull them apart, you have to do work, right. And so this potential is what determines how much work you have to do to pull them apart or push them together. So the greater the depth of the potential well, essentially the more work is involved in disturbing the particles from their equilibrium position of separation. So these are also known as van der Waals forces of interaction. Although the van der Waals is a term that's more commonly associated with atoms and molecules, but it applies equally well to particle pairs as well. And the surface energy is again involved in how these forces actually operate. I mean, basically if you bring two high surface energy particles together, their attractive forces are going to be greater than their repulsive forces, relatively speaking, whereas if you have two low surface energy surfaces coming together, they are going to want to naturally repel each other, right. So the quantities A and B are very much a function of the surface energies of the particles involved, and thereby the Hammacher constant also. So that is where the surface energy of the particle enters this equation. However, the r to the power 6 and r to the power 12 dependencies in the denominator apply no matter what the particles are, whether it is high surface energy or low surface energy. The qualitative feature of this curve does not change. What changes is, again, as the surface energies increase, the point of closest approach will become smaller and smaller. So the equilibrium position will be one that essentially involves the two particles virtually in contact, whereas as the surface energies decrease, de-equilibrium becomes longer and longer. So the equilibrium position for the particle pair is to be farther apart when you have low surface energy particles compared to when you have high surface energy particles. So these are links that you have to be clear about in your mind. You know, when people talk about surface energies of particles and they talk about the Leonard-Jones potential, there is a link between the two, which is very, very basic, very fundamental to how particles and molecules behave when they approach each other. And as you can see, these are very much characteristics of the surface. The core or even the subsurface of the particle really doesn't enter either that equation, you know, that where we calculated the surface energy of the particle, or these equations where we are looking at the potential between a pair of particles. It's all based on surface characteristics of the particle. Now the third aspect that we are going to discuss is the third aspect that we will discuss is the adsorption of fluids by particles. Now this is another important aspect of particle to medium interaction, because what we have talked about so far is primarily interaction between two solid surfaces or two liquid surfaces that are entrained in a continuous medium. But even before they interact with each other, first they have to interact with the medium that they are suspended in. So let's look at some of the equations that govern the interaction between the particle and the fluid medium that it's suspended in. Now there are obviously four cases of possible interactions. You have a liquid droplet interacting with a gaseous environment, you have a liquid droplet interacting with a liquid environment, or you have a solid particle reacting or interacting with a liquid environment, and you have a solid particle interacting with a gaseous environment. Different principles of transfer apply in each case. For example, when you have a liquid droplet that is exposed to a gaseous atmosphere, the primary mode of exchange between them would be absorption of the gas by the liquid and evaporation of the liquid to contribute vapor molecules, which then get mixed in with the gas. When you have a liquid droplet that is suspended in a liquid medium, now obviously that only makes sense when you have immiscible liquids. So if you have an immiscible liquid droplet that is suspended in a continuum of another liquid, we call these emulsions. And here also the primary characteristic is that the droplet that is suspended has surface tension characteristics which prevent the macroscopic liquid medium from wetting it, so that essentially there is a repulsive interaction that is set up between the emulsion droplets and the liquid in which these droplets are contained. Now the third case of a solid particle that is suspended in a liquid medium, again it involves two transfer processes. One is absorption of the liquid by the solid and dissolution of the solid into the liquid. The dissolution part and the evaporation part we will study later in this course. Now when we look at liquid take up by the particle through an absorption process, that is essentially a surface tension driven phenomenon, and here actually the subsurface can come into play, because how much liquid can be absorbed by the particle very much depends on the capillary volume that is available in the subsurface region. As we sketched in the last lecture, when you have capillaries, whether they are blind capillaries or interconnected capillaries, they provide a path for liquid to get transferred into the surface using surface tension as the mechanism, and therefore essentially the more porous the particle, the more capillaries that are present in the subsurface, the higher will be the amount of liquid that can be taken up by the particle. The fourth case is actually the most interesting in the sense of adsorption of gases by a particle. There are many industrial applications that involve, for example, catalysis and heterogeneous surface reactions, where it is necessary for a surface to actually adsorb a gas molecule in order to promote a reaction that takes place on the surface. So there has been tremendous interest in looking at the various phenomena governing the uptake of gas molecules by surfaces as a function of pressure especially. And one of the names associated with adsorption of gaseous molecules on surfaces is Langmuir. I am sure everyone has heard of the Langmuir isotherm. Now the Langmuir principle states essentially that only one monolayer of gas molecules can be adsorbed on the surface. That is really what distinguishes the Langmuir model from the various other adsorption models such as the BET model, for example. So in the Langmuir scenario, you can only adsorb a single monolayer of gas molecules on a surface. Langmuir also stated that as far as adsorption is concerned, each location on the surface is equivalent to any other location. So there is no preferential adsorption of the gas molecules on any part of the surface. The probability or efficiency of adsorption is uniform across the entire surface that is adsorbing the gas. The third assumption in the Langmuir model is there is no interaction between the adsorbed molecules. So once a molecule has been adsorbed, it does not even know that its nearest neighbor exists, so that the subsequent processes all become interaction between the adsorbed gas molecules and the surface on which the gas molecules have been adsorbed. And the fourth assumption of course is monolayer adsorption. In other words, once a layer of gas molecule exists on the surface, you cannot adsorb a second layer on top of the first layer. So with these four assumptions, Langmuir formulated his model by assuming that an equilibrium position or an equilibrium situation will prevail where the rate of desorption from the surface equals the rate of adsorption on the surface. That is the central principle behind the Langmuir model. Rate of adsorption equals rate of desorption at dynamic equilibrium. So let's consider a case where you have some species A that is getting adsorbed on the surface. Let's say that Na is the number of molecules approaching the surface, and let's say that a certain fraction of them stick to the surface. Let's call that some Fs. So this is the fraction of the molecules approaching the surface that actually stick to the surface. And let's say that F is the fraction of surface on which molecules have already adsorbed. So F is fraction of surface covered by the adsorbed molecules. And finally, let's say that RA is rate of desorption of species A from the surface. So given these parameters, now how do you define this equation here? How do you equate the rate of adsorption to rate of desorption? Well, rate of adsorption is going to be equal to Na multiplied by Fs multiplied by 1 minus F because 1 minus F is the fraction of the surface that is available for further adsorption, and this has to be equated to F times RA. So, if you group the terms, so this basically means Na times Fs minus Na Fs times F equals F times Ra, or Na times Fs equals F times Na Fs plus Ra, or in other words F is equal to Fs times Na divided by Fs times Na plus Ra. Now, if you look at this parameter Na, which is a number of molecules approaching the surface, for a given temperature, this parameter is primarily dependent on pressure. The greater the pressure that you exert, the more will be the number of molecules approaching the surface. So, since Na is proportional to P, you can actually rewrite that equation as F equals some Kp divided by 1 plus Kp. So, this relates the fractional coverage of the surface to the pressure that is prevailing in the system. Obviously, the constant K will incorporate the Fs and Ra terms in it, as well as the actual multiplier that converts pressure into Na. But regardless, in terms of the qualitative relationship, F equals Kp by 1 plus Kp is the classic Langmuir isotherm or Langmuir adsorption isotherm as it is known. If you plot P versus F, how is it going to look? For very high pressures, Kp will be much greater than 1, F will tend towards 1, right. So, let us say that this is 1, so it should approach 1. At very low pressures, it is virtually 0. I mean, if there is no pressure, that means there is going to be nothing pushing the molecules toward the surface. So, the curve basically looks like this. So, you may all be aware of the shape of this isotherm, but it is very important for you to realize how this was obtained. It is a simple dynamic equilibrium balance, mass balance. Rate of molecules arriving equals rate of molecules leaving. So, it is important that you should be able to derive the Langmuir isotherm from first principles. Now, the other model that has become quite popular is the BET model, Brunauer-Emmett-Teller model. The only difference between the BET model and the Langmuir model is the BET model allows for multilayer adsorption. So, that is the only assumption out of the 4 that I had listed earlier, which is relaxed for the BET case. Now, if you look at the adsorption equation in the BET model, again the pressure plays a key role. But the adsorption process itself is related in terms of an adsorbed volume of gases on the surface. Okay, instead of fractional coverage of the surface, which does not make sense when you are considering multilayer adsorption, we use volume of adsorbate as the metric, and this is written as Kx divided by 1 minus x times 1 minus x plus Kx, where x equals P over P0, where P is the prevailing pressure and P0 is the saturation vapor pressure of the adsorbing species. So, in the case of the BET model, if you plot P versus adsorbed volume, what kind of shape would you expect? It turns out there are actually 5 major classes of BET curves. the first one actually looks very similar to the Langmuir model. This essentially is the simplest case where multi-layer adsorption proceeds in a manner that is very analogous to single layer adsorption. So, this is one. Now, another model is a case where you essentially do this, but then you again rise in the amount of adsorbed material and you establish a new plateau. Now, when can something like that happen? What is the physical implication of a curve like this? This is a case where subsurface adsorption begins after the top surface is saturated. So, this subsequent increase in the adsorption amount is related to subsurface coming into play, and the fact that it reaches another plateau implies that there are two adsorption plateaus here, one corresponding to the surface and one corresponding to the subsurface. So, this is the second model of BET adsorption. So, which particle will follow which model depends on the nature now not only of the surface, but also of the subsurface region of the particle. The third model is one where you again go through an initial plateauing effect, and then the further adsorption proceeds without necessarily showing a plateauing behavior. Now, when would this happen? Here not only is the surface involved, but also the subsurface and the core of the particle also gets involved in the adsorption process. So, essentially the adsorption continues until the entire particle is basically transformed, right. So, this is a case where the subsurface is such that there is almost a direct path from the surface to the core or interior of the particle. So, the extent of adsorption is much greater in this case compared to the first two. Now, all of these are what we call physisorption processes. The process by which the gas molecule is getting adsorbed is purely physical in nature, but as we know, when you have possible chemical reactivity between the two surfaces, well, between the surface and the gas molecule, then chemisorption will come into play also. Chemisorption is not even addressed in the Langmuir model. However, the BET model does address chemisorption specifically, and the BET scenario suggests that when you have chemisorption going on, you will see a behavior that is very, very different from any of these. What type of behavior would you expect in the case where chemisorption is happening? The curves kind of flip around. In the case where chemisorption is going on, initially the sorption is very, very poor, but then there is a sharp knee that happens, a sharp bend in the curve. Once chemisorption begins, the increase in the chemisorption rate is just tremendous, and it essentially goes to completion. In other words, the entire particle gets saturated with chemisorbed material very rapidly, because chemisorption being a chemical process, the core will actually react even more than the surface and the subsurface, because it is a purest representation of the material. So, this curve 4 primarily reflects chemisorption as a significant phenomenon. And finally, the fifth variation on the BET is a case where you essentially have a combination of chemisorption and physisorption, so that initially you follow a physisorption kind of a route, followed by where chemisorption takes over. Now, this would happen in cases where the surface itself is relatively inert with respect to the adsorbed molecule, but the subsurface and especially the core regions are much more reactive to the adsorbed gas molecule. This can happen, for example, when the surface is poisoned with impurities, which greatly inhibit the reactivity of the particle material to the surrounding gas stream. But once you go below the layer where the impurities are concentrated, the chemical reactivity is greatly enhanced. So again, these 5 potential behaviors of BET adsorption isotherms are very, very important to understand. And you should be able to discuss them in a physical sense, understand the mechanisms involved, understand what is going on, and be able to talk to them in reasonable detail. Now, we haven't really talked about the effect of temperature. So what would happen if you have a surface that's adsorbing gas molecules and you increase the temperature? What is going to happen? There will be more desorption, right, in general, and therefore the amount of adsorption typically will decrease in the case of physisorption. In the case of chemisorption, it might actually increase exponentially, because if the chemical reaction becomes the dominant phenomenon in dictating the adsorption, then you will see an exact reverse behavior. In fact, a test that scientists use to assess whether physisorption is dominant or chemisorption is dominant is simply to measure adsorption at various temperatures. If there is a chemisorption dominance, you will see increased adsorption at higher temperatures. If there is a physisorption dominance, you will see a reduced dependence at higher temperatures. So what we have discussed so far are 3 very, very basic phenomena that represent how a particle interacts with its environment. In the next lecture, we will discuss some of these aspects in a little more detail. The particle to surface adhesion is a very, very critical phenomenon which plays a huge role in many manufacturing industries. Similarly, particle to particle cohesion plays a huge role in determining properties like the flowability of a suspension, stability of suspensions, and so on. So in the next 2 or 3 lectures, we will focus on particle adhesion to surfaces and particle cohesive behavior to each other.